So today we are going to do the Romberg integration that I have been saying you that we'll do, and we are going to discuss the theory and the background behind how Romberg integration works. So we are going to limit our discussion of the Romberg integration only to the trapezoidal rule. Romberg integration can be based on even the Simpson's 1/3 rule, even the Simpson's 3/8 rule, but then we'll only use the trapezoidal rule to um, see how the Romberg works. So let me write that down here. Trapezoidal rule. Okay. Now in the last week we have seen the Richardson's extrapolation formula, and if you remember, we said that if you have n segments and you have two n segments, if you derive the approximate value using the n segments and the two n segments, then you can use them to get a better approximation using the Richardson's. So let's say the approximated value using the trapezoidal rule is in for n segments and I2n for 2n segments. And then we can find a better value or the true value for this integral using in and I2n, and that would be approximately equal to I2n plus I sub 2n minus in divided by 3. So this was the Richardson extrapolation formula. And if you remember, we calculated the Richardson's extrapolation based on the true error of it being approximately proportional to 1 over n squared. So now if you continue doing this, you will get better and better approximation. For example, let's say I have n segments, 2n segments, 4n segments, and 8n segments. Now we can use these here to get better approximations, right? Let me just do it a bit better. So we can use these approximations here to get better values. And this one you can say it is approximated using the multiple segment trapezoidal rule, which is in. This one is I2n, and this here is I4n, and this here is I8n. And you can use the in and I2n to get a better value for the Richardson approximation. And here also you can approximate a better value. So these values here, you will be getting it using the Richardson's extrapolation. So this is called the first order extrapolation. And the error here, the true error here is approximately proportional to 1 over n squared. Now, what Romberg says is that let's take it several steps further. These approximations that we did using the Richardson's, let's do these steps more. So let's take more of these two and get a better approximation here. And let's take this two here, get a better approximation here. And maybe let's take this two here and get a better approximation here. So that's what is Romberg doing. But then, so this one here is the second order extrapolation. This is the third order extrapolation. But here we know that the true error is this one here, that is approximately proportional to 1 over n squared. But for this here, we don't know what is the true error approximately proportional to. Neither for this we know. All right. Now let's go ahead and see how do we do this. Also, I'd like to say you that for the Richardson's extrapolation, you know that the formula is I2n plus I to n minus in divided by 3. But for this one here and this one here, the formulas will not be the same. It will be different. So we have to derive these formulas here. Now, the true error for the Richardson's extrapolation, you can say, or the first order extrapolation, is 1 over n squared, which is also, you can say, this is as equal to being h squared, because 1 over n is nothing but the width of the segment, and h is also the width of the segment. So you can replace the 1 over n squared with h squared here. So the exact true error for multiple segment trapezoidal rule can be written as, maybe I'll just write that down. The exact true error for multiple segment trapezoidal rule can be written as the true error is equal to a1 times h squared plus a2 times h to the power 4 plus a3 times h to the power 6 plus continuation. So I'm showing this to you without proof. The proof is out of the scope of this class here. And this here is the first order of true error that is proportional to h squared. So here you can see this one is the first order extrapolation, and that the true error here is proportional to h squared. And here you can see this is the second order extrapolation, and the true error here is equal to h to the power 4. And then here is the third order extrapolation, and the true error here is h to the power 6. So a1, a2, a3 are not necessarily constants. They are based on the derivatives of the functions which you are integrating, and it's based on where you are calculating those derivatives. But this is a little bit more complicated, and I'm skipping it because it's no point talking to you over this. What we have to basically focus or concentrate on is the true error. What is the true error proportional to? So in the first order, the true error is proportional to h squared. In the second order, the true error is proportional to h to the power 4. And in the third order extrapolation, true error is proportional to h to the power 6. That's what you need to know. Okay, so now let's say that we have n segments, 2n segments, and 4n segments. And we approximated the value using the trapezoidal rule here, which is I of n, I of 2n, and I of 4n. All right. Now, using the Richardson's, the formula will be I to n. To approximate the value here, it will be I to n plus I to n minus in divided by 3. And here it will be I 4n plus I of 4n minus I 2n divided by 3. Okay. Now, until here, did you all follow up? Do you all have any doubts? Any doubts until here? Clear. Okay. So let's go ahead.
Yes.
Yep.
Why do you use y to n? Why not in?
For which one here?
For
For
the
this
first
one
one.
here?
No. You wrote y to n plus I to n minus in divided by 3.
Okay. So
Why did you add I to n to the I to n minus I1 divided by 3?
I've shown you this in the Richardson's extrapolation. How do we derive the formula? So this is the formula for Richardson's extrapolation, where
Okay.
you have like how do you say? You have the double the segments of n. When you double the segments, you use it here and here. But then the derivation of this I have shown you in the Richardson's.
Okay, thank you.
You're welcome. Just follow up there, and if you have doubts after that, I can discuss to you later on. No problem. So now let's say that this one here, let's name it as Jn. So let's say this here is equal to Jn, and this one here is equal to J2n. Okay. And for even for the person, I don't know who asked me the question. I'm so sorry. Even for you, it will get clear. Your question will get clear even later in the Romberg discussion. After some time, I'll clear to you why I used I2n and not in. You will get cleared. So here let's say this is equal to Jn, and let's say this is equal to J2n. And now if we use Romberg to approximate the value of the next extrapolation, we'll get here J2n plus J2n minus Jn divided by 15. So why did we get 15 here? Or how did we get 15 here? So we'll discuss it in some time. Before that, I would just tell you that the true error here is approximately proportional to h square, and the true error here, as we just saw with the above equation, here it is approximately proportional to h to the power 4. Okay, now let's go and see why we got here 15 and not 3 like before. So if you look at the true value for Jn, it is approximately equal to Jn plus c divided by n to the power 4. And if you now double the number of segments, the true value will be approximately equal to J2n plus the constant divided by 2n. I'm replacing the n by 2n now to the power 4. So now as you're doubling the number of segments, the true value is proportional to n to the power 4 here. And if you double the number of segments here, the true error is not going to be quartered, but 1/16. As you can see, 2 to the power 4, that's 1/16 here. And if you solve these two equations and the two unknowns, you will get here true value will be approximately equal to J2n plus J2n minus Jn divided by 15. Okay, now if you feel lost that from where I got this one, from where I got this one here, please go back to Richardson's extrapolation class. You will understand from where I got all of this. Okay, because this is a continuation from that lecture, so I don't want to repeat. Now, here, now if you look at, so this one here is for the second order extrapolation. If we look at the first order extrapolation true value, it is equal to, or the formula, it is equal to I to n plus I to n minus in divided by 3. So what you can do here is you can write this one here, the 15. Okay, first let's discuss how did we get the 15, right? So we got the 15 because here we have 2 to the power 4. That's 16 minus 1 here. So 2 to the power 4, 16 minus 1 here, which is 15. And we can write this 15 as 4 to the power 3 minus 1 minus 1. And we can write this one here as 4 to the power 2 minus 1 minus 1 here. So this one here is the first order extrapolation. And for the first order extrapolation, the value up for 4 to the power what here will be 2. And for the second order extrapolation, the value here will be 3. Then let's say for the third order extrapolation, it will be 4. For fourth order extrapolation, it will be 5, and so on. Okay, now the Romberg integration is going to look like, in general formula, it will be I of k comma j is equal to I of k minus 1 comma j plus 1 plus I of k minus 1 j plus 1 minus I of k minus 1 comma j divided by 4 to the power k minus 1 minus 1 here. So that's the Romberg general formula. Now here the k is equal to, or you can say the k is the order of extrapolation. So if you say k is equal to 1, you're talking about the average values that you derived through the trapezoidal rule. And if you say about k is equal to 2, it is the values that you got using the Richardson's extrapolation. And for J is the less accurate estimate. I think I'll not be able to write the word here. So the less accurate estimate. And J plus 1 is the next accurate estimate. Now, it might be a bit of work to follow the indices of the formula. So we will write down the indices in the tree, and then we'll do the example by following the tree. So I'm sure you're getting a bit confused here how this formula is working. But then now, if I draw the tree, most probably it will get cleared, and I will even answer the question of, I'm not sure whom. Let's see. So, okay, now let's start making the tree here. So we said that, let's say we have some average values that we got using the trapezoidal rule. So let's say the first one, the k, as we know, for trapezoidal rule, the k is equal to 1, right? So here we have k is equal to 1, and let's say the first j is 1, and then it increases down. So the k is always equal to 1, but the j is 2 now. The k is still 1, and the j is 3. So these are different average values are received using different segments, that is n, 2n, 3n, and 4n. So here k is equal to 1 and j is equal to 4. So this one here, k is equal to 1, okay, for the trapezoidal rule approximations. Now if we use this two to approximate, here for the next part we have k is equal to 2 now. All right, so now we have here I will be k is equal to 2, so 2 here, and j is equal to 1 for this 2. And then we will, when we approximate this to here, we have I is equal to 2 comma 2. The j is increasing, this is the j plus 1, the next one. And here we have I is equal to 2 comma 3. And then for the next approximations, where k is equal to 3 now, we have here I is 3 comma 1 and I is 3 comma 2. And then for the next one we'll have I is 4 comma 1, where k is equal to 4. So here this is the first order approximation, the second order approximation, and this is the third order approximation. So this is what we get using the trapezoidal rule here, and this is what we get using the Richardson's, and then the next ones are using the Romberg. So is this clear to all of you until here? So let's answer the question, right? So here, if you have using the formula, if you're finding out or trying to find out for the first one, let's say for k is equal to 2. So this is a separate work here. So let's say for k is equal to 2 and j is equal to 1. If we are finding now I21, according to the formula, we'll have, for the first one, we'll have here I of k minus 1 and j plus 1. So I k minus 1, so 2 minus 1 is 1, comma j plus 1, 1 plus 1 is 2. So for finding out, okay, I'll do that later. So here plus we have, next one, let's look at the formula. We have I of k minus 1, j plus 1. So we have I k minus 1, 2 minus 1 is 1, j plus 1 is 2, minus we have I k minus 1 comma j. So k is 2, 2 minus 1 is 1, comma j is 1, divided by, we have 4k minus 1 minus 1. So 4 to the power k is 2 minus 1. So I'll just write it as 1 minus 1, which will be 3. So is this now clearing the doubt why we had I2n here and I2n here? Because we are taking here, like now what I showed you over here, the formula is basically deriving the formula for I2 of 1, right? So when we're deriving the formula for I2 of 1, we are using I1 2, 1 comma 2 first, and then we're subtracting I1 comma 2 minus I1 comma 1 divided by, this is equal to 3. So is your doubt clear now?
Yes, miss, thank you.
You're welcome. Okay, so now once we are clear with the tree, now we can go ahead and solve an example. Okay, now so the vertical distance, the vertical distance in meters covered by a rocket covered by a rocket from t is equal to 8 to t is equal to 30 seconds, so 8 seconds to 30 seconds, is given by x, where the integration is from 8 to 30, and the formula is, or the function is 2000 ln times 140,000 divided by 140,000 minus 2100 t minus 9.8 t dt. So use Romberg's rule to find the distance covered. So we'll use the Romberg's rule here to find the distance covered. And we'll use 1, 2, 4, and 8 segment of the trapezoidal rule. So let me write it down here. So we will, let's say we have a table where we have the segments 1, 2, 4, and 8, and we have the approximated values as 11868, 11266, and we have 4 ones and 3, and 11074. So now if you want to write it according to our table here, we would write these here, or we can just say this one here is I1 comma 1, this one here is I1 comma 2. So these are all our k is, for all of them k will be equal to 1 because these are all approximated using the trapezoidal rule. So here it will be I of 1 comma 3 and I of 1 comma 4. Okay, so the 4 values here correspond to using 1, 2, and 4 and 8 segments of the trapezoidal rule respectively. And now to get the first order extrapolation values, we'll work it out. So let's work out for, as you know, the formula here. So we'll first work out for I21, then I22, and I23, right? So we've got these 4 values, and we'll work out this 3 here for the first order extrapolation. So we'll have here I21. The formula will be I1 comma 2 for it, plus I1 comma 2 minus I1 comma 1 divided by 3. So I1 comma 2 is here 11266. So we have here 11266 plus, again we have 11266 minus I1 comma 1, which is 11868. So we have here 11868 divided by 3. This gives you the answer as 11065. Now for I2 comma 2, can you write me the equation for I2 comma 2? Write me the equation for I2 comma 2. Do you need the table? Okay, we have I1 comma 3 plus I1 comma 3 minus I1 comma 2 divided by 3. Is that correct? That's correct, Ryan, and even for Aisha, it's correct. Just the brackets are missing. Okay, that's correct. So let's go ahead and work it out. So we have I1 comma 3 plus I1 comma 3 minus I1 comma 2 divided by 3. So for this, we have the values as 11113 plus 11113 minus 11266 divided by 3. So this is equal to 11061. Now we'll find out the third approximate value for the first order approximation, which is I23. So here the formula will have I14 plus, so for I23, let me show you. So for I23, we will be using I14 and I13. Okay, so I14 plus I14 minus I1 comma 3 divided by 3. So here, using the values given to us, we have 11074. So that these values I'm taking from this table here. So I1 comma 4 is 11074. So here we have this one here plus 11074 minus 11113 divided by 3. This gives us the value 11061. So we have solved this already using the Richardson's extrapolation in the last class. The new thing that we'll solve is the for the second order extrapolation. So all we have done up till now here is for the first order extrapolation. So we have got the first order extrapolation values, and now we will work out for the second order extrapolation. Okay, so for the second order extrapolation, we have I31 and I32. So for I31, we'll be using I22 and I21. But here, the 4k will be different, right? So k is equal to 3. So we'll have, for this one here, it will be divided by 4. K is 3 minus 1, which will be 15. Okay, so don't forget that. So here now we'll have for I3 comma 1, we'll have I2 comma 2 plus I2 comma 2 minus I2 comma 1 divided by 15. So from the table we have here the values as this one's here. So we have 11062 minus 11065 divided by 15, which is equal to 11062. Maybe let's write the values what we got here in the table. So I'm not sure if this is a good idea or not, but or maybe I'll just take the whole table, copy paste it somewhere else. So let's copy the table here. So for these values here, we got this one is equal to 1. No. So we have here this one, it was given to us. So we had here 11868. And then this one here is 11266. And here we had 4 ones and 3. And here we have 11074. We have derived these values here. So 2 1, we have got it as 11065, and for 2 2 we got 11062, and here we got 11061. And now we just calculated I3 comma 1. What happened? Okay, I3 comma 1, where we got 11062. So we have 11062. Can you all calculate the value of I32 and give me? Calculate the value of I32 and give me. For I32, we have 11061. Okay, correct, correct. Okay, that's correct. Great. Okay, so here we have 11061, and in the meantime, calculate the value for R41 while I'm writing it for you here so that when you have the notes, you know what is done. So we have I32 is equal to I33 plus I2 comma 3 minus I2 comma 2 divided by 15. So I want the value of I41 from all of you. Okay, so this one here is equal to 11061 plus 11061 minus 11062 divided by 15. That is equal to 11061. So now we'll go for the third.
Miss,
Yes.
Something there is wrong. It's I23, not I33.
Yeah, correct. Thank you. Thank you. Okay. Okay, great. So now we have for the third order extrapolation. So for this we have I4 comma 1, which we have here is, okay, I still made a mistake here. So that's supposed to be I2 comma 3. Okay. So here we have I3 comma 2 plus I3 comma 2 minus I3 comma 1 divided by, okay, I didn't still get values from you, or I got, but I don't see it because it's the same. Okay, you gave me the values. Yeah, it's correct. It's correct. Okay, so so I think, I'm not sure if you know. Let me ask you. So what is the value for, what is the value here? What did you all get? 63. Great. Yes. So we have here 4 to the power 4 minus 1 minus 1. So that is 4 to the power 3 minus 1, which is 63. So this one here, the value is 63. Correct. Great. Perfect. Okay, that makes me really happy because you all are following. You're all with me. Okay, so the answer here, I don't have enough space to write all the values. I'll just give you the final answer here, which is 11061. And as since we are finding the distance covered, so the unit is meter here, m. Okay, and let me write also the final values here. So here we have 11061. So this one here is first order approximation. Here we have the second order approximation, and this here is the third order approximations. Okay, and okay, just a second. So okay, it's because I want to write down here that this one here was for one segment, for one segment. This one here was for two segments, and we had here for four segments, and here for 8 segments. Okay, so did you all understand Romberg's method? This is the end of Romberg's method. Did you all understand? Do you all have any doubts anywhere that I need to clarify now before we move on to the next topic? Okay, everything is clear. Great. Okay. Okay, great. Okay, great. So let's go for numerical differentiation now. Okay, so here we are going to talk about continuous functions. And to estimate the value of the derivative of a function numerically, we have three uh, approximations that are suggested. So the first one that we are going to look at will be forward divided difference approximation. You can say method. So these are methods to approximate the derivatives, and the first one that we are going to look at is forward divided difference approximation method. So for this, we need to draw our, let's say we have a function that looks like, one second. Okay, so our function looks like this. So here we have f of x, and here we have x. So we have a function, let's suppose like this one here, and we have to find out the derivative at this point here, x. So this is where we have to find out the derivative of the function. And what we do is we choose a point which is delta x ahead of this point. So we choose a point which is delta x ahead of this point. So let's say this point is here. So this point here is x plus delta x. The distance between them is delta x. And then what we'll do is, so again, what we're trying to do here is we're trying to find the first derivative or the slope of the function at the point x here. And the reason why I'm doing this is because I'm using the definition of the f prime x. So f prime x, that is equal to limit of delta x approaching to 0, f of x plus delta x minus f of x divided by delta x. So here you have learned this in your differential calculus class. This is the definition of the derivative of a function. But for forward divided difference, we are not going to use the limit of delta x going towards x, because delta x going or approaching to 0, because if you are choosing delta x approaching to 0, you can always choose smaller delta x. So we want the delta x to be finite, and we are going to consider this same definition of the derivative of a function, but without delta x approaching to 0. So we'll write it as the derivative of the function here is equal to f of x plus delta x minus f of x divided by delta x. So here delta x is finite, and because delta x is finite, so we know that we'll get a truncation error here, right? So because we are approximating a mathematical procedure by this formula here. Now this one is the formula for the forward divided difference. So it's really easy. You got the formula in some seconds. So I hope you understood and you're with me. If you are lost, please tell me. Okay. So we have got our formula for the forward divided difference, and I've represented it as FDD. So that's F for forward, D for divided, and D for difference. So now let's work on an example. So we have a function given to us here, which is 2 times e to the power 1.5x. And we have to find out the derivative of this function where x is equal to 3. So let's write our formula again. So we have for the forward divided difference, f dash x is approximately equal to f of x plus delta x minus f of x divided by delta x. Okay, so here we are supposed to find out the derivative at x is equal to 3. So that will be equal to or approximately equal to f of x. For us, x is 3. It's given to us plus the delta x. So delta x is maybe either given to you or you have to choose a value for delta x. So here let's choose for delta x 0.1. So we'll have here 0.1 minus f of x, which is 3, divided by delta x, which is 0.1. So this one here is equal to f of 3.1 minus f of 3 divided by 0.1. So this is nothing but the slope of the function at 3, which is the rise divided by the run, correct? So the rise from 3.1 to 3. So you're going from 3 to 3.1 for the rise. And for the run, also the same thing. So if you subtract 3.1 minus 3, you get 0.1. So this is nothing but the slope of the function at 3. So here we have 2 to the power e raised to the power 1.5 times 3.1 minus 2 times e to the power 1.5 times 3 divided by 0.1. And that gives us the approximated value of 291.35 for the derivative of the function given here. Up till here, is it clear for everyone? Okay, great. If it's not clear, please let me know. Okay. Okay, great. So let's go ahead now. So in order to be able to see how good this method of forward divided difference is working, let's calculate the exact value, right? From the differential calculus knowledge that we have, and then we'll see what kind of true errors that we are getting. So for the exact value, let's write the function at first. So the function is 2 times e to the power 1.5x, and the differentiation of it, we'll get it using this formula here. So d over dx of e to the power ax is equal to a times e to the power ax. So if we use this here, we get here 2 times 1.5 e to the power 1.5x. Okay, so that is equal to 3 times e to the power 1.5x. Now we have to find out the derivative of the function at 3. So that will be 3 times e to the power 1.5 times 3 here. So that is giving us the exact value as 270.05. So that's the exact value of this derivative of this function up to 5 significant figures. So now we saw that for the f prime 3, we got the value approximately as 291.35 when we took delta x as 0.1. And for the same f prime 3, we got it equal to 270.35 when we say delta x is approaching 0. Alright, so now we can calculate the true error, which is true value minus the approximated value. So the true value we have is 270.35 minus the approximated value, which is 291.35. That is equal to minus 21.30, and the absolute relative error will be here 7.88%. So now if I decrease the delta x value here from 0.1, if I halve the value, what is going to happen to the true errors? So let us see that one now. So what if I decrease the delta x? Let's see what we'll get for the function at 3 and what will be the true error. So we took 0.1. So our function is still the same. Our f of x, the function is still 2 times e to the power 1.5x. So when we take 0.1, we saw we got the value at 3 is 291.35 and the error was minus 21.30. Now if you halve the x value to 0.05, you get the approximation as 280.43 and the true error as minus 10.38. And if you halve this again, 0.025, you get here the approximation is 275.18 and the true error is 5.127. So you can see that as we are kind of decreasing the delta x, we are reaching the exact value here, 270.05, right? And maybe one more thing that you can see over here is that as you halve the value of the delta x, the true error value is also getting approximately half. Okay, so that's the end of the forward divided difference. Now we'll go for the next approximation that I told you about. So we have, for the next one, we have the backward divided difference approximation method. So for this one now, again, let me draw the function. So here we have f of x, and here we have x, and our function looks something like this one here. So we have to find out the derivative of the function at this value here, x. And now for this one here, we will go back delta x and take another point. So we'll go back delta x here and we'll take another point. Let's set this point here, which is x minus delta x. because this is backward divided difference, so we take a point back of x. So here we have the difference, or the distance between both x and delta x minus delta x, is delta x here. So I'll draw a secant line from this point to this point here. So okay, and from here to here to find out the slope. So here we have the rise, and the rise is, here we have f of x minus f of x minus delta x. And for the run, as you can see, it is delta x here, right? So that's the run. So now again, we'll go back to the definition of the derivative, which is f dash x is equal to limit of delta x approaching 0. We have f of x plus delta x minus f of x divided by delta x. So here, for the backward divided difference, we will use, instead of the plus x, we'll use minus x here. So, and remove the limit. So we'll get over here for f of x the rise, which is fx minus f of x minus delta x divided by the run, which is delta x. And this is the formula for the backward divided difference. Okay, so if you substitute in this formula here, instead of plus delta x minus delta x, you will get exactly the formula that I wrote down. And now, if you again look at our example, so we'll again go back to our example here. So the function is same, which is 2 times e to the power 1.5x. And we have to find out the derivative of the function at x is equal to 3. And we chose the delta x to be 0.1. So if you look in the formula and we try to find out for f dash of 3, we'll get f of x. So f of 3 minus f of x, which is 3 minus delta x is 0.1, divided by delta x, that is 0.1. Okay, so we have here f of 3 minus f of 2.9 divided by 0.1. Can you all give me the value for this one here, for the approximation of the first derivative of x at x is equal to 3 using backward divided difference? Give me the answer. To 50.77. Yes, that's correct answer. So we have here 2 times e to the power 1.5 times 3 minus 2 times e to the power 1.5 times 2.9 divided by 0.1, and that is equal to 250.77. Okay, so now again, let's go ahead and calculate the true value. So for f dash, or you can say f prime of 3, we got approximately to 50.77 when we took the delta x to be equal to 0.1 in backward divided difference. And we know that this is exactly equal to 270.05 when you take the delta x approaching to 0. Can you calculate me the true error and the relative true error for this one here now? So the true error is correct, yes. And what is the relative, absolute relative true error? So here we have true value minus approximated value, which is 270.05 minus 250.77. That is equal to 19.27. And the relative error is 7.13%, 14%, 139%. All those are correct, but whether your answer is wrong, Ryan, you forgot to multiply by 100. Okay, looks overall correct. So we have here 7.138%. So you can see that the forward divided difference and the backward divided difference, the error is quite similar. They have kind of, for forward divided difference, we got the error as 7.88%. And for the backward, the error has decreased a bit, which is 7.138%. So not much of a difference here. So let's try to see one more, or before we go to one more, let's see what happens when we decrease the value of x here for the same function. So here, what if we get for delta x and for f prime of 3 and true error. So we're decreasing the delta x values and seeing what happens here. So for 0.1, we just got 250.77 and the true error is 19.27. Then if we halve the value here, we get 260.17, and here we'll get 9.88. And then here, if you halve it again, 0.25, you get 265.05. And the true error we get is 5.00. So again, if you halve the value of the delta x, the true error is getting halved here. And as you decrease the value of delta x, the true error is decreasing and the answer is approaching the exact value, which is 270.05. All right. Now, I want to ask you a question. That is, if true value is not known, what if we did not know the true value here? What if we did not know this one here? How would you use the concept of, or let me write the question down here. So, if true value is not known, how would you use the concept of absolute relative approximate error, that is EA, to find values correct up to some significant figure or some given significant figure. How would you use that? So if the true value is not known to us, we use the EA to get to know exactly how many significant figures of the answer we can trust, right? So for this table here, let's calculate the EA. And let's see, you can already see it over here clearly how many significant figures you can trust, but still just for you to understand it better, what is EA? Can you calculate for the first one here? Can you calculate the EA? Can you calculate the estimate error for delta x is equal to 0.1?
Miss, we cannot calculate it for 0.1
Yes, because we
because,
don't have a previous value, right?
yes,
Yes, great. Okay, so now can you calculate and give me the value for this one here for 0.05, the EA, the approximate error? 3.61%. Any other answers? Okay. Okay. So I haven't calculated this one here. I'll just take your values. So you're saying me this one is 3.613%. So this is in percent. Okay. What would be the EA for 0.025 delta x? Okay, now calculate me the delta x for, sorry, EA for delta x is equal to 0.025. So we'll take the present value 265.05 minus the previous value, which is 260.17, and we'll divide it by the present value, which is 265.05, and then multiply it to 100, and that will give us, okay, 1.84%. So here we have 1.84%. So as you can see that this one here is less than 5%. So yes, we can trust here one significant figure. And as you can see it from this value also over here, we can only trust the first significant figure that's matching to the original answer, right? So the concept of true value and approximate error, I hope it is clear to you all now, the true error and the approximate error, right? Okay, so now let's go to, so we have answered this one question here. Now let's go to the central divided difference approximation method. Okay, so I'll draw the function again. So here we have f of x, and here we have x, and the function we can say it looks like this one here, and we have to find out the derivative of the function at this point here, which is x. Now, what we have to do for the central divided difference is that we have to take a point which is ahead of x here somewhere, and that will be x plus delta x, and also we have to take a point behind of x which is somewhere here, which is x minus delta x. So the distance between these points is delta x, and the distance between these 2 points is also delta x. Okay, so now we will draw the line from this point here to this point, and also same we'll draw it here. So we'll have the rise, which is f of x plus delta x minus f of x minus delta x, and the run here will be 2 times delta x. So we have 2 times delta x as the run. And then if you're writing the formula down now, we can write it here. So the first derivative of x will look like this one here. So the rise is f of x plus delta x minus f of x minus delta x divided by the run, which is 2 times delta x. So that's the formula for the central divided difference approximation. Is it clear to all of you? Do you have any doubts?
Miss,
Yes.
why did you use the limit in the first two derivative and you did not use it here?
Okay, we have used it here. It's not like I didn't use it here. So I have used the, what is it? Okay, wait. So, okay. I did use the definition. So that is the definition of the derivative. That's f dash x is equal to limit going from the x approaching 0, and the definition is x plus delta x minus f of x divided by delta x, right? So we have used this definition only, but then we have we have found out our rise and run, and we have replaced the rise and run of the definition using ours, and then we have also omitted the limit from x delta x going or approaching to 0, and then we have made the delta x for us finite. So we have used the definition to arrive at our formula for the central divided difference. I hope that's clear now. So again, if we go to our example, we'll take the same function, which is 2e to the power 1.5x, and we'll find out the derivative of the function at 3, which is, we don't know, of course, and delta x, we chose it as 0.1. So, one second. Okay, so it seems like two of the students have left the class. I hope you're on time whenever I give the quiz. So there is a quiz, all of you know that at the end or anytime I want, I can just give you a quiz. So yeah. Now here our formula for the central divided difference is equal to or approximately equal to f of x plus delta x minus f of x minus delta x divided by 2 times delta x. And if you're finding the approximate value of the derivative of the function at x is equal to 3, we'll have f of x is 3 plus delta x is 0.1 minus, again we have x is 3 minus delta x is 0.1 divided by 2 times delta x, which is 0.1. So can you give me the value for this one here? So here we have f of 3.1. I'm waiting for your answers. So here we have f of 3.1 minus f of 2.9 divided by 0.2. So now if you put that in the function, you have 2 to the power 2 times e to the power 1.5 times 3.1 minus 2 to the power 2 times e to the power 1.5 times 2.9 divided by 0.2. So that is equal to what? Okay, correct. That's correct answer. So we have here 271.06. And now we know that the exact value of this function here is 27.05. Can you calculate me the relative true error and give me the answer? Okay, correct, everyone. So now I want you to calculate the relative true error, absolute relative true error, and give me the answer. I want relative true error, Ryan, not just the true error. The true error is correct. So the true error is minus 1.014. That's correct. What I want is I want the relative true error. So that's absolute value of 270.05 minus 271.06 divided by 270.05 times 100. So that's correct answer, Rauda and Ryan. That's correct. So we have here 0.375%. Now, if you remember, what was the relative true error for backward and forward? We had something 7 point. So for forward divided difference, we had 7.88%. For backward divided difference, we had 7.13%. And now for central divided difference, we are having 0.375%, which means that this is way more closer to the exact solution, right? So why did this happen here? Let's have a look maybe. So if you have the delta x here and f prime of 3 here and the true error. So here if you have the delta x as 0.1, 0.05 and 0.025, the f prime of 3 gives you the answer here as 271.06 that we have calculated. Then we have for the next one 270.30, 270.11, and the true error is minus 1.014, minus 0.2532, and minus 0.0630330. So what you can see here is when we are halving or we are dividing the delta x by 2, the true error here is now getting quartered, not halved like for central divided difference and backward divided difference, but quartered. So that is one of the reasons why we have arrived to a better approximation using the central divided difference rather than forward divided difference and backward divided difference. So is everything clear until now?